Hi, I'm Alessandro, and I'm part of one of the two groups that has been developing the project Journey in Robotics, which is an activity that aims to give practical examples that could be useful to integrate with the theory presented in class. Specifically, our project has consisted in producing a series of light scripts using MATLAB in order to eviscerate every aspect of the robotic arm we chose. We chose a thrilling planar arm as the focus of our journey, and we ended up producing 8 output files which discuss every theoretical aspect we have seen during the lectures, and implement it with step-by-step examples and the possibility for the end user to customize and obtain various simulations via the modification of critical parameters. As an example, in the first part of the work, we addressed the Denavit-Artermer convention and the direct and inverse kinematic as well. And for every topic, as I'm doing right now, the end user is able to change the parameters and see in real time what differs on every instance. Along our whole code, we have made extensive use of the robotic toolbox made by Peter Cork, since it provides a pre-made function and classes useful to represent orientation and pose in 2D and 3D, and many ways to address kinematics and dynamics.
The topic that I want to present is related to the first concepts presented in the course. After having described the manipulator through the Denavit-Artermer convention, it is possible to move to a study under the kinematic point of view. The concept of direct kinematic is introduced with the help of an animation, where the user can vary joint coordinates to easily see what happens to the end effector. Therefore, we wanted to highlight the problem of multiple solutions. That is something we need to be aware of when tackling the inverse kinematic problem. It is also important to remember the different way that is needed to proceed when redundant manipulators are analyzed. In the following part, the user can simulate the behavior of the 3D manipulator getting through the elbow singularity. Notice the full extended setup that characterizes this configuration and see what happens to the velocity ellipsoid in this particular situation. A final section to show the importance of using the damped least square method when analyzing a robot getting close to singularities. On the one side, it can be seen that joint velocities tend to infinity, whereas on the other side, velocity profile stays in a limited range, thanks to the damping parameter that, if increased, masks the effect of singularity, worsening though the accuracy of the obtained result.
In this chapter, you can find all about the dynamics of the 3-link planar arm. This MATLAB file is completely customizable, and you can choose all the parameters to see their different effects. First of all, you can choose the pose between some noted examples, the joint variable, or the initial and final position of the end effector. Then, you can choose between a cubic or a trapezoidal trajectory. Finally, you can find the dynamics of the manipulator by setting the forces and torques. Once all the parameters are set, a lot of diagram will be shown. You can analyze separately the effect of inertia, the Coriolis effect, the gravitational effect, and the external environment. You can also decide to study each joint separately to enter in more depth of manipulator behavior. At the end, an animation of the complete manipulator is shown, and you will have all the instruments to study the dynamics in an easy and interactive way.
Last but not least example that we are going to give to you is about the topic of controlling manipulator. In particular, we analyze the decentralized control, where each joint is controlled independently from the others, and considering the dynamical coupling as disturbances. In accordance with the philosophy of our work, we initially described the theory behind it, and then we implemented application examples. In particular, we analyzed the influence of the transmission ratio. In fact, here there are some examples starting from KR equal to 1 to KR equal to 100. In addition, we create for the user custom simulation in which the user could tune and change the value of the transmission ratio, the value of the proportional gain for position feedback, velocity feedback, and acceleration feedback.